Hi people, in this video I'm going to explain the apparent curvature of the Earth that we see from higher altitudes within the Earth. There is a masterful illusion at play, and now that we know we have this radiation pattern exhibited or mimicking this dipole antenna that is originating from the octahedron in the center of the Earth, we can understand how light is actually operating and giving us the illusion that the horizon is actually curving convexly. And so I believe this is going to clear up a lot of things within the whole Earth-shaped debate community where, flat earthers are arguing over whether or not there is curvature to the horizon versus the ball earthers who believe that there is. Well, they're partially correct. There is an apparent curvature, and it is an apparent convex curvature to the horizon the higher you go. So within this little chart that I created here, I called it the altitude versus the apparent curvature guide. And I took that radiation pattern. If you see this gray curve, this dipole curve here coming from the center, what I did was I replicated that figure 8 curve basically. I turned it every 15 degrees, and what you end up having to happen is that it creates these intersection points. And so we know that the radius of the Earth is approximately 4,000 miles or 3959. And so we can judge the distances of these intersection points. So if I zoom in real close here, we'll see an intersection point at 80 miles, one at 400 miles. I also created one especially for the 250-mile International Space Station altitude. I have one at 1350 and approximately 1980. And what I ended up concluding here is that you see the way these periphery lines emanate outward like that. Like the yellow line is going to kiss the edge here at this intersection point and along this intersection point as well. So from that viewpoint, theoretically, you're getting a view of the Earth, or a range of seeing this much of the Earth. If this was if straight across would be 180 degrees, and so this is roughly maybe 100 and I think it's 150, I want to say. And so at that point, probably a little bit higher, that's where we have the geostationary satellites. If you watched the previous video, I showed you how satellites like the Himawari 8 are actually giving very subtle indicators that we're looking inside the concavity of the Earth, with the light flaring out along the edges, the sunlight flaring out along the edges, as well as the amount of darkness as the sun supposedly goes behind the Earth, where we would be, theoretically, we would be seeing more darkness. I'll put that link in the description box. But going back to this graph here, we can take those intersection points, and with our dipole radiation pattern, we can find out where those points interact the celestial sphere. And what I'm doing with the celestial sphere in the center is I'm actually doubling it as a little sky chart. So if this is your point of view here in the center, the top half would be the sky, and the line area, that would be the ground. Okay, so this blue line, this is at 0 feet or 0 miles altitude. And so we're not getting any curvature whatsoever. And so that is also how the celestial sphere, how it actually splits the celestial sphere in two. See the blue line, it perfectly bifurcates like that. So as we get higher, we'll look at this salmon colored line here. That's at 80 miles. And so we see our range here. See the dotted lines, salmon colored lines here? That's our range. So I simply took that curve of the outside of this outer circle here, which is the Earth, and I brought it down. I shrunk it and I brought it down to connect to the salmon colored lines here on the ends here. So this is the curve. It's the same curve. I just shrunk it, and so I fitted it so it fits perfectly in there. So that's the amount of curvature that you would see, apparent curvature, mind you, apparent convex curvature, mind you, from that altitude. And so if you notice here how these lines are intersecting the celestial sphere, the blue line, the salmon, the purple, the green, the pink, the yellow, that's divided up into every 15 degrees, I believe. Yeah, 15, let's see, 15, 30, 45, 60, yeah, every 15 degrees. And so I calculated the amount of sky versus the amount of ground or earth that you would see. Like from at this altitude, you would see more sky. There would be, it would be about 58% more sky, or actually 58% sky versus, the remainder being the ground. And so the higher you go, the more sky you're going to see, or the elongation of the sky. I was watching this video here. Let me pull it up really quick here. The Star Trail video from the ISS. I believe it is up above the glass. That's why we actually can see the glass sky here. But I was noticing that the star trails looked more erect, as opposed to when you see the star trails from the equator. They seem like they're curving more, and so we're getting an elongation of the sky, and so that helped me conclude that is why we're getting that elongation, is because we're seeing more sky and less Earth the higher we go, and that actually creates the illusion that the Earth is a planet or a sphere. From that, like I showed you, well, they will show you from the Himawari 8 footage how the Earth will look like a sphere, but it's not a sphere. I'll put this link in the description box too. I show you all the anomalies that prove, and they're very subtle, but that prove it's not a sphere. But it'll give you the illusion, the optical illusion that it is a sphere. And so the higher you go, like with this green line, it's at 850 miles. That's going to intersect over here, and so I just took that range where the green dotted lines are, right? See, right over here versus right over there. And so I took this curve from green to green, from dotted green to dotted green. I shrunk that down, and I fitted it right into there. And so that's the curve. That's the curve that we would see from this vantage point here in the center. So we're at 850 miles high, and we're looking down at the Earth. We're getting 75% sky, and the curvature of the Earth appears to curve convexly, and you get that illusion that you think it's a planet, you think it's a sphere, but you're actually inside the sphere. So moving on, we go a little bit higher to 1,350 miles. We get this pink line. Zoom back out a little bit here, and we notice how the pink dotted line, the range, is from here to here. So we get this curve. This is pretty self-explanatory. And so I took that curve from pink line to pink line, and I shrunk it down, and it fits right into there. Now, obviously, we're getting more spherical. And so the yellow line, obviously, is from this yellow dotted line all the way to this yellow dotted line. Just I took this curve here. And so from that distance, 1,980 miles, we're getting almost half of the Earth from this. See this yellow line here, and we're seeing 91% sky. So the Earth is appearing to shrink exponentially, as if it were a planet. And obviously you can't get any further to this point here, or the celestial sphere point, where the Earth would theoretically disappear into a dot. Maybe this is where they're getting the term black hole. This is the event horizon of the black hole. Who knows? But anyway, theoretically, and that's also taking or noting that there could be a caveat here with the glass. That could be actually, it is actually, it's enlarging the sizes of the planets from our vantage point down in Earth. But theoretically, this is how it is working. This is how the apparent curvature is displayed or created the higher you go like that. It's based exponentially, so if you get, like I said, if you get higher than 1980, let's say this is like 3000, you know, you're going to get a curve like this blue curve, so you're only going to be able to see half of the Earth like that. So this is going to shed a lot of light on this whole debate, you know, flat versus globe, and neither are true. But the indications are that we are getting a slight curvature. I was looking around a little bit here, this video here by Kara. She shows that even with a fisheye lens, you're still getting, as long as you find center of the image, you're still going to get a straight line. And so the higher you go, like this footage here, I mean, even though it's with a wide-angle fisheye lens, if you get the horizon to go right into this, to intersect the center point, you're still going to see a slight convexity to it. And so this is what flat earthers will deny, but I'm not going to deny it. Actually, it works perfectly if you understand how the bending light works. So the space station, we get this amount of curvature. I'm assuming that this is not a wide-angle lens as well. I mean, we see some of the station silhouetted in the foreground, and it does not look like it's, well, it might, who knows, but like this, see, that doesn't look like it's distorted with a wide angle. But regardless, we are seeing a curvature. It is false curvature. It's false curvature, right? I mean, even with you can take one of those theodolite applications and you go up in an airplane, you will see the horizon descend slightly. And keep in mind, when you see the horizon descend like that, you have to conclude that you're going to see curvature. If that horizon is not at your eye level, you're going to have to see curvature. It's indicating that there's going to have to be curvature. But this is the divine illusion at play. The truth is that you're inside the concavity of the Earth. Light is bending upward with this radiation pattern, this dipole radiation pattern, because we have an octahedron in the center. And the curve, or the distance, the higher you go, the apparent size of the Earth decreases exponentially, and the curve of the horizon curves according to these figures here. So I hope you guys can have enough objectivity to see this, because this is the only way it works, and this brings solution to the whole Earth-shaped debate. You're viewing a curve, you're seeing a curvature, but it's a false curvature the higher you go. Okay, I'm gonna make a nice high-res graphic of this and put it in the description box as well, so you can look at it. Thanks for watching.